Hello, this is your recap video for Monday's lesson. The topics we did on Monday were, we talked a little bit about binomials. That's something we started on, scratched the surface on, which is basically just multiplication of two things. Binomial meaning two numbers, binomial. Combinations, so we talked about where the binomial coefficients come from, and Pascal's triangle 1, 1, 1, 1, 2, 1, 1, 3, 3, 1, and so forth. Where they come from and how they can be calculated. And you said, oh, I'll just press this button on a calculator and it appears. So we talked about that and its effect on probability, which leads, leads us to the coefficients of the binomial expansion. Then we looked at two particular things, the binomial square and the cube. So that's when we're squaring something or cubing something, like x plus 1 squared or x plus 1 cubed. If we do x plus 1 squared, we get x squared plus 2x plus 1. And we'd look at the picture of that, so just to see what that looks like as an actual square. And then did the same thing with the cube, and we saw that if we choose x to be 10, that means it's 11 squared, so it's 121, or if we choose for the cube it's going to be 11 cubed, which is 1331, which is its volume. And we're going to talk about how the graph of a quadratic, the square, represents the area of a square or a rectangle, hence the name quadrilateral, quadratic, because it gives you either a rectangle or a square. And same for a cubic, so it's giving you the different values of the volume for your choice of x. So we talked about that, and then finally I showed you what happens if we employ this binomial square by saying, okay, I'll start off with a square, increase it by a little bit. What happens? What's the change? And that the whole process is called differentiation. So that was just an introduction to that based on the binomial stuff that you've learnt already. So I'm just going to recap those things again for you to go over so that you've got it recorded as well as in the notes I left with you. Okay, so first up we have lottery. So we talked about lottery and asked if there are 49 numbers to choose from, 1 to 49, how many possible combinations of 6 numbers are there? So 1 to 6, 1, 2, 3, 4, 5, 6, or 1, 2, 3, 4, 5, 7, or 41, 42, 43, 44, 45, or 9, 15, 16, 18, 23, whatever. All the possible combinations of all those 49 numbers. When you just choose 6, how many different ways are there of organising those numbers? And you put it into your calculator and you got put 49C6. 49C6. So in other words, 49 is a number of numbers we get to choose from, and we just want 6. And it'll tell you how many combinations there are. And if you recall, it was 13.9 million. So that means that since there are 13.9 million possibilities, there's 1 in 13.9 million chance that you'll win if you just buy one ticket, which is obviously fairly unlikely. And it's much more likely that you won't win. In maths, remember, we like to look at all the possibilities, right? And then from that we can assess the probability, what's probably going to happen. But we need to know what all the possibilities are to do that. The other example I showed you or talked about was imagine that you had a part-time job where you could work any day, Monday to Friday, and you only have to work 2 days a week. It's up to you when. How many different choices have you got? So we wrote down what they were: Monday, Tuesday, Monday, Wednesday, Wednesday, Thursday, Wednesday, Friday, all the different ones. And it turned out there were 10. And the reason for that is for the same thing, which is 5C2. I've got 5 to choose from. I'm choosing 2. How many possible ways are there? And we get 10 from that. Again, you can put that in the calculator. So what I didn't actually mention what the formula was for that. So the formula is that you just use 5 and 2 essentially. So we talked about factorial and what factorial was first by I asked you how many ways are there to organise ABC. And remember we figured out that it was 3 ways to organise the first letter, 2 to organise the second letter, and 1 to organise the last one, because there's only 1 letter left. So there's 6 possible ways, which was known as 3 factorial. So this possible ways of doing things is used in combinations, which makes sense, doesn't it? Because we're trying to figure out how many different combinations there are. We need to know how many possible ways there are to do something. So again, we're concerned with the possibilities. So 5c2 would be 5 factorial divided by 2 factorial, the choice that we're doing, and then the difference between the 2 factorial, so 5 take away 2 factorial. That's the formula for combinations. So which kind of makes sense because factorial gives us the number of ways of doing something. And that turns out to be 10. 10. So 5 times 4 times 3 times 2 divided by 2 times by 3 by 2, which works out as 10. If you want to work that out yourself, pause the video, work it out yourself, make sure that it is 10 rather than using the calculator. So write out the factorial, so 5 times 4 times 3 times 2 times 1, and see if it does actually give you that. And then the last question I asked you is that at least one boy. So remember I said that this lady, this imaginary lady, has 2 children, and at least one of them is a boy. What's the probability that the other one is a boy? And you fell into the trap and said 50-50. But remember, it's not that. Can you remember what it was? So the answer was 1 in 3. And you think, well, how can there be 3 possible ways? Well, it's because we want to look at all the possibilities. So either this lady has 2 boys, or she has a boy and a girl, but she might also have a girl and a boy, and you might think, well, they're just the same thing, which is true, but there are 2 possible ways that she could have at least one boy. Either it's the oldest or the youngest, so that's 2 possible situations, isn't it? And therefore it's a possibility. And the other one is girl-girl. That's the other thing she could have. So she could have 2 boys, boy-girl, girl-boy, or girl-girl. And again, notice that pattern. 1 for the boy-boy, 2 for the girl-boy situation, 1 girl-girl. So boy-boy, girl-girl, boy-boy, girl-boy, or girl-girl. It goes 1, 2, 1, and hopefully that's a familiar number to you, and one that I told you is very important. Because it just comes up so often. It's a binomial square. 11 times 11? 1, 2, 1. And you can see that here in this even simple example about imaginary ladies with their children. But it comes up in algebra a lot. It's the most kind of fundamental number that comes out of any algebra. And we've actually been doing it in different ways already. So yeah, so why is it at least one boy? Well, why is it 1 in 3? Well, because there's 3 possible situations. If she has one boy, what's the probability that the other one is a boy? Well, that's that situation. But in total, there are 3 situations where there's at least one boy. The other 2 are just girls, though, so it's 1 out of 3 possible things, means the probability is 1 out of 3. So like I said before, we look at all the possibilities, and from that we can determine the probability. That's what the binomial is very good for. Here I've jumped forward to the binomial expansion itself, and I've replaced the coefficients with their combinations. So the whole idea of using these combinations is that they correspond by Pascal's triangle. So 3C0, which we've got 3 things to choose from, and I choose none of them. How many ways are there to do that? Well, there's only one way to choose nothing, so that's 1. And it's x cubed, because the first power we put is on, I put a different colour just to highlight it, is 3. And then we're going to put the other thing in the binomial, which is 1, and times it. And that power is going to be 0, because the 2 powers always add up to 3. And it starts at 3, then cascades down, and it starts at 0 and goes up. So that's the pattern. It's a symmetrical pattern. Symmetry is very important in maths, so that all makes a lovely bit of symmetry, and we'll see the symmetry again with the coefficients. So it's 1x cubed, or just x cubed. 3c1 is, I've got 3 to choose from, and I choose one of them. How many ways are there? Well, there's 3. Either the first one, the second one, or the third one, because I'm just choosing one out of the 3, aren't I? So if it was A, B, C, and you can choose any letter of A, B, C. Which one do you want? you've got three choices, A, B or C. So that's 3. This becomes x squared, and 1 to the power 1 is 1. 3c2 is also 3 because for the three letter situation, A, B, C, AB, AC, BC, they're my three choices, aren't they? So that's 3 as well. X to the 1 is x, 1 squared is 1. And then with 3c3 is, I've got 3 letters to choose from and I'm choosing 3, so I've only got one choice, A, B, C. So that's 1 times x to the 0, which is 1 times 1 cubed, which is 1. So notice the symmetry there, 1, 3, 3, 1. Line of symmetry down the middle. The powers go down, so 3, 2, 1, 0. Powers go up, 1 to the 0, 1 to the 1, 1 squared, 1 cubed. So it's entirely symmetrical. And that's like the fundamental binomial cube. So anything else, if I put that x plus 2 in, all that really is just the same thing, but the 2 gets cubed instead, and the 2 gets squared instead, and the 2 goes to the power 1 instead. So we get a kind of multiple of this kind of fundamental binomial just by putting a 2 in there. It still retains the same features, it's just scaled up. Be a good idea if you tried that and compared it. So if you pause the video and do x plus 1, x plus 2 cubed, compare the two and you'll see it's just a scaled up version of this. Then we looked at the binomial square. So I said that imagine we had a square which was 10 by 10 and increase the sides by 1. What happens? Well, the new area becomes 121 because the area of this is 100, the area of this is 10, the area of this is 10, the area of this is 1. So we end up with 1 lot of 100, 2 lots of 10, and 1 unit, 1, 2, 1. Then I said that we're concerned with the change, how much has this square changed in size? And the answer is by 21. It's got 21 bigger. But remember the video, we can ignore that little square here because relatively it's small. Okay, in this example it's not small, but when we actually use it in reality it is too small to worry about. So the change is 20. And if we compare 20 to the actual original size of the square, which is 10 by 10, we notice the change is twice the original side length. So twice L, 2 times L. If this length L, 10, could be any number, so it could be x, then it's 2 times x, isn't it? So it's 2x. So the change, when you increase a square by 1, you get a new area, and the change in that area is twice the original length of the square, no matter what we start off with. So what you did was you then went, okay, what if I increase 11 by 1? So you compared 144 to 121, took them away. 23, take the 1 away in the corner, it's 22. That's twice 11, which makes sense because it was 11, now it's 12, so it's twice the original length. And we did a few, and you notice that pattern was true throughout. It's twice the original length. The change in the area is always twice the original length of the previous square. So if we start off with a square, which is 10 by 10, it's got an area of x squared, where 10 is now x. Just call that length x, and we call that length x. The area of the square here is x squared, isn't it? Then if we change that square by 1, there is change in area per step is 2x, twice its original length. And that's true because we saw it for 10, we saw it for 11, we saw it for 12, we saw it for 13, and so on. So it turns out it's true for any value we start off with. If we increase the square by 1, the change in the area per step is twice the original length. Okay, that's probably the very first thing you'll learn when you do differentiation at school, except they won't explain it like this. They'll explain it in a different way because that'd be too simple. The way they'll explain it is that you use a rule and it'll always give you the answer no matter what you start off with. But I like my students to see what you're actually doing, and all we're doing is making a square bigger. If we start off with a cube and make that bigger by 1, we saw in the video, remember that everything increased by 1. and we looked at the pattern of it, and what happened there was the cube, x cubed, when you increase that by 1, that generates a binomial expansion of this. Because there's my x, I've increased it by 1, and I cube it, I get this thing. And we said we're only concerned with the change, so that means I get rid of what I started off with, which was the cube, and that leaves me with 3x squared plus 3x plus 1. Then I said, well, this 1 we don't pay any attention to because it's too small to worry about. And this actually will be too small to worry about as well in the big scheme of things, so that can go. So the change in the volume per unit step, is 3x squared. Okay. And if you keep doing that for all binomial expansions, say you do it for x to the power 4 and increase the x by 1, do the binomial expansion. Why don't you have a go at that? Do the binomial expansion of x plus 1 to the 4, write it out, take away the original x to the 4, see what you get, and see if you can spot a pattern or a rule that's starting to develop. So if you can do that for next week, that would be great. I'm sure that you'll spot it. You're very good at pattern spotting. Sorry, too far. And that's it. So I'll send you the video of the pictures, the one with the square and the cube changing in size. The way he explains it I don't really like very much, but it's got brilliant graphics, so it's great for visualization, so I'll send you that. And I'll see you next week.